Hello everyone, I'd like to welcome you to my presentation about memory allocation in software diversity in our prototype called MAD for memory allocation diversity. This is joint work with former student of mine, Manuel Wiesinger, present student Daniel Dorfmeister, and myself, Stefan Brunthaler. So why are we all here? I think it's quite simple. Well, no price defense prevents against trespass style attacks, and I also personally don't think that none of the prior defenses that were published in the last couple of years scales towards recognizing and preventing trespass style attacks. So ever since I first learned about Rowhammer attacks from Victor van der Wind's talk in Drama talk in 2016 at CCS in Vienna, I looked into the anatomy of Rowhammer attacks together with some of my students. And what we found is that Rowhammer attacks often proceed in 3 stages. The first stage is a reconnaissance stage, basically trying to figure out where the bit flips are. In the second stage, we have a templating massaging stage where we're trying to construct a vulnerable configuration. That means the pages that the attacker needs to control in order to induce bit flips. And then the third part is to coerce a third party to put sensitive target information into the expected location such that if the attacker holds or controls the vulnerable configuration, he can induce bit flips. So if we look into the reconnaissance and massaging stages, they can actually be combined into one stage for some of the attacks. We find that there are mostly 2 strategies at play. The one we call sparse allocation massaging and the other one dense allocation massaging. And memory spraying, just for completeness, is a combination of both strategies, and I'm going to get back to spraying later on. Sparse allocation massaging we're defining as a massaging technique where the attacker allocates as little memory as possible, or he's not only allocating, but he's controlling as little memory as possible. One of these techniques, for instance, is Fist Feng Shui, other one is memory chasing. And some of the reviewers asked, why is this Fist Feng Shui from Drama? And for Drama, he tries to exhaust all of the memory, but he does so, or the attack does so, in a way that is basically forking a lot of processes, and these processes are trying to allocate pages, but if the allocated pages are not the vulnerable configuration that the attack is looking for, the process terminates, and that basically means that the pages are going to give back to the memory allocation system. The dense allocation massaging means where the attacker allocates and holds on to, this is the operative part, to as much memory as possible. For example, Flip Feng Shui. In order to defeat these massaging techniques, we have the following observation, namely that the attack cannot succeed or is at least deterred significantly. That means protracted and prolonged in the temporal domain if it never obtains any new blocks. So what this means is that if we can constrain the pages that the attacker operates onto a small set of pages, then the attack will not succeed or will take substantially longer. And for dense allocation massaging, what we find is that it's essentially a brute force technique that co-opts specific operating system behavior or browser behavior and so on and so forth. Now on to diversity. Why are we talking about diversity in this space? The predominant use of diversity is against code reuse attacks. There have been other domains like cache side channels in the paper that we wrote in 2015 that explores how this works in the cache side channel domain. And whenever we talk to other people about this defense, then usually what comes up is, how can this be efficient? This a memory subsystem is a low entropy domain. How can diversity be successful in that space? And in order to illustrate this point, keep in mind that, for instance, in a 16 gigabyte system, there are only 4 million 4 kilobyte pages, and 4 million for a brute force attack is actually not that much. So how are we going to look into this? MAD is addressing this low entropy problem by combining 2 novel spatial diversification techniques. One is called horizontal diversity and the other one vertical diversity that I'm going to show later on. And both of them are used to increase block recycling. So basically constraining the amount of memory to the reviewer, the amount of memory to constrain the attack to a small amount of memory. The overall MAD architecture is as follows. We have MAD sitting in the middle between the processes and the memory allocator. In our case, this is a body allocator that manages physical memory, but we don't have any memory allocator specific, so this could also be a free list. And MAD also has no operating system internal, so MAD could also be used in a database system or a browser or any other system. So there are no specific layout here. MAD itself consists of two types of caches, so-called allocation caches that serve allocation requests and shadow caches that hold freed pages. And then we see that all of these allocation and shadow caches are in specific orders, similar to a body allocator. So we see that they have order 0 to order 3, so from 4 kilobytes to 32 kilobytes for illustrative purposes. So in the actual implementation, we have up to order 10. So how does horizontal diversity look like? So here we have a couple of memory allocation requests. We have a fully filled allocation cache and an empty shadow cache. So we have an alloc, and that basically means that we select a random page from the allocation cache. So this is what has been allocated. Now we start freeing, and freeing does exactly the same. We put the freed pages into random positions in the shadow cache. And now if we get another alloc, what we see is that the allocation cache has been drained, so it's not full anymore. So the likelihood of using a random offset and trying to find a page gets lower and lower. And so what we now do in horizontal diversity is that we're moving these pages back to the allocation cache again. So basically we're horizontally recycling this, and now this cache is full again, and now we can serve allocation requests again. In vertical diversity, we extend this horizontal idea to a vertical idea, and this is illustrated as follows. Now we have this cache one has been drained, so now we take one from a higher order. It need not be the next order, it can be any higher order, and we split them up again. And so, like I said, this works across orders, and so we can ensure that we have enough pages in the allocation cache. And we've also had, once we found this out, we also found that we can extend this to inverse vertical diversity. So when we find bodies in one of those caches, we can merge them and thus keep these pages in our system again. So again with this, and this also works across orders. So how effective is this at battling or deterring sparse allocation massaging? So we ran this experiment where this is a textbook body allocator in a kind of a memory chasing algorithm, and this is what the attack looks like when we use MAD. So this is with the MAD configuration. And what we see that there's a vast difference in numbers when we compute what we're calling the page loss ratio. We find that we average over 1 billion allocations in 25,000 case steps. Then MAD gives you about 0.35 pages every 25,000 allocations, whereas without MAD you get 1.5 pages, so roughly the four times as many pages every 25,000 steps. So if you do the numbers, you'll find out that for a 16 gigabyte system, that means you need a maximum of 77 billion allocations to enumerate all pages, and that actually grows by an order of magnitude to almost 300 billion allocations in order to enumerate them. And what we found interesting also, there is like a 900 million allocations plateau without any significant increase in unique physical blocks allocated. So that means at this stage, we have roughly enough pages that we can serve all of the requests from the attack without requiring new pages. So now let's look from sparse to dense allocation massaging. Could you not still exhaust all memory? And the short answer is yes, you can. It's brute force attack. But the long answer is, wait a minute, let's look at this into more detail. So a dense allocation massaging means that the attacker is allocating lots of pages. So what this means is that the allocation cache is going to be drained because the attacker is allocating many pages. And once he's allocated all of these pages that we've seen here, what we're going to see is that now we're using horizontal diversity to refill the allocation caches again. And now with all of those pages having been moved, what we see is that allocation requests can now consume all of the pages again and drain the allocation cache. And as a result, what we find is that both caches are empty. Those need to be refilled from the body allocator or from the underlying memory allocator, and the other ones are always empty. And so we see this with a high frequency that we need to refill those caches a lot, and those caches will be empty in a dense allocation attack or memory massaging attempt. And conversely, if you go back to a spraying attack, you allocate a lot of memory, but not enough to let the operating system use the OOM killer or something like this. So you need to allocate them, and you need to free them again. And when we free this memory, the memory that the attacker held onto in a spraying attack, we find that the shadow caches are going to be filled again. And once those shadow caches are full, horizontal diversity is going to move some of those pages over to the allocation caches. And once this has been done, we also need to make sure that the freeze will again put blocks into the shadow caches. So if you free like a third of memory, then these caches will be full, and then eventually these caches will be full. So now there are no allocations, so this remains full, and there is no space left, meaning that whenever you want to free a new page, you need to take some of these pages and put them back to the body allocator. And again, this is something that we see with a high frequency. So what we find is that MAD effectively acts as a signal booster that identifies these asymptomatic configurations. And because MAD is restricted to a small memory area, what we find also is that the more samples we collect, the higher resolution picture we get. And in addition, we find that if the attacker adapts to what these asymptomatic configurations are, then we're frustrating his attack, because the attack is going to be protracted because we battle MAD, or the attacker has to battle MAD recycling, and also the detection monitoring. So it's like, either way the attacker needs to adapt to this situation, the way he needs to adapt to the way he needs to adapt his attack to what MAD does is going to make the attack worse. So let's look at the security evaluation. We did a worst case analysis, a probabilistic one, where we assumed that the attacker can place a vulnerable block into MAD's caches, and then how many allocations are needed to obtain the vulnerable configuration. So what we find is that with the attacker using a multitude of different allocations, so here he allocates between 4,000 and 8,000 blocks, 8,000 and 16,000, and so on, fourth blocks. So this is a lower bound and upper bound. We find that on average he needs, with this least amount of page blocks that he's allocating, he needs on average 600,000, roughly 600,000 allocations, and this decreases to about 250,000 allocations if he allocates these blocks. That's the average that we found. The median that we computed is much lower, and this is because this is a probabilistic system. So there are some configurations that take an enormous amount of time, but the median looks like this. And interestingly, the lowest amount, so it does not steadily decrease, but the lowest amount is actually between 32,000 and 64,000 allocations, or memory allocations performed, and then we need that many requests. So I think this is already, assuming that you somehow find a vulnerable configuration and put it into MAD, this is how many allocations you'll need. So this brings us to our contribution slides. I think the two biggest takeaways from this paper is, or from this work is, it's first of all still work in progress, and it's diversity-based defense, meaning it's a probabilistic defense. So some of the attacks may work, and other attacks may not work anymore. So for me, the two biggest takeaways, or the two biggest contributions are as follows. The one is the generalization result. It's the first step towards a software-only diversity-based defense against Rowhammer. So this is quite big, because again, it generalizes the principles underlying diversity from code reuse attacks to other attacks. So this has been one of the biggest things that I'm concerned with in the past couple of years. And the second one is effectiveness. So we find that horizontal and vertical diversity combine to actually effectively cope with low entropy domains. So even though there are only 4 million blocks, and brute force is viable for this small amount of blocks that you can deal with some sophisticated kind of spatial diversification, you can still get an order of magnitude higher power out of the system. And so I think this is what the biggest takeaways and the biggest surprises for us have been when doing this research. If you have any questions, please ask later on. Other than that, thanks for the attention and have a great day.